I'm Ahmed, and this session will be the continuation of the last session. We are discussing the logistic regression parameters, and in the last session we have discussed till the intercept scaling. Okay, so in this session we will start from class weight. Okay, in the class weight parameter, you can pass the values in the form of dictionary, or you can also pass a the value balanced. Okay, and default is none. So weights associated with the class. It is generally used in that case when you have a data set, and let's say in the case of binary classification you have just two values 0 and 1, two classes 0 and 1. Okay, and you have some knowledge that this class has more weight, is more important than the class 0. Let's say class 1 is more important than the class 0. Okay, then you can mention specifically in that parameter that class 1 should have this weight and class 0 should have this weight in the form of dictionary, class label, and the weight. Okay, if you will not give that, all classes are supposed to have weight 1. All means all classes should be considered as a uh, considered as a same weight or have equal importance. Okay, then there is also another option in the here that you can use balanced mode. Balanced mode, this is balanced mode, uses the values of y to automatically adjust weights. Okay, so it will adjust weight values, or give weight to your classes according to the frequency of their appearance in the samples. Okay, and they have given that formula. N samples divided by n classes into np dot bin count 1. Okay, we will explore this, let's say in this way. I will take a screenshot from here. Mm, okay, so we can discuss it here. Okay, let's say you have a y. You have a data set. This is your data set, and on this side you have your independent variables. Okay, and this is your dependent variable. Okay, let's say you have in that way why you have 10 you have total 10 samples. Let's say you have total samples is equal to 10. Okay, your number of samples are 10. So here you have values 0 0 0 0 0 3 to 5 6 7 8 9 10. Let's say you have 10 values here. I can make it in this way. This data set you have, let's say, and your here, keep in mind I am discussing when the class weight has value balanced. Okay, when it has value balanced. Otherwise, it will give the weight to, if you will mention by yourself in the form of dictionary. In the form of dictionary, if you have mentioned that this class has this weight, then it will get by itself. And if you will not mention, then it will be weight 1. Now, the third case that I am discussing here. Okay, in the case of balanced. So let's say you have a data set in which your total number of samples are 10, in which number of, let's say number of zeros are 8, and number of ones are 2. Okay, you have here 8 zeros and 2 ones. How it will work? It will give the weight to each sample. Let's say n samples, this formula to use, n samples divided by n number of classes into np dot bin count. Np, it's numpy, and it is using numpy bin count function. Okay, so here passing y. First, I can do it how it works. Np dot bin count, I will tell you here. Bin count here, if you have y, so it will count the values, okay, at the index. Let's say you have just you have just two classes here, okay. So 0, 1, okay, you will have this type of array. Against the 0 index, it will be here mention the frequency of zeros. Against the 1 index, the frequency of ones in that y, okay. So if you will calculate np dot bin count of that y, this will give you that array, okay, that array 8 comma 2, okay. Now how many samples you have? 10 total samples. How many number of classes you have? Two classes, and here will be 8, this array. When you will multiply, this array will become 16 comma 4, okay. So if you will make here 10 divided by 16 and 10 divided by 4, okay. So what will be the value of 10 by 16? It will be about 0.625. And what will be 4? It will be 2.5, okay. And this is, it's a 0 index and it's a 1 index, its first value is 0 and second value is 1, okay. So in this way, it will give when you have this class weight, when you have this class weight is equal to balance, and you have this data set, then your zero class will have weight 0.625 and your one class have weight 2.5, okay. In this way it calculates. Now the advantage of this doing this is, you can see here how many samples you have for in which zeros. There are 8 samples. 8 into 0.625 will become 5. And in the case of uh, how many number of samples which have class 1, they are just 2 samples. So here it will become 2 into 2.5. Here you can say by giving this weight, okay, this is actually removing the strength of unbalanced data, okay. The data visually seems like it's imbalanced, but when you will give some assign some weight that class 0, class 0 has weight 0.625, class 1 has weight 2.5, then this unbalanced data converted into balanced data by strength, okay, not by physically, by the strength, it become a balanced data set, because both zeros and ones now have equal type of strength. Now what is the advantage when you are training your model and you somehow you know that you have imbalanced data, but you want that your model will not be affected by imbalance your imbalanced data, okay, due to imbalanced nature of your data. It can be affected by the values of independent variables, but it should not be affected by the imbalanced nature of your data. Then you can do that type of you can use this type of values for your parameters to make your data set strengths as a balance, so that your model will not be affected by the imbalanced nature. Understand? So that's why usually uh, how this class weight is equal to balance works in that way. This formula to use actually, okay. In this way it works, that I have explained you. And what is advantage? Advantage is that it actually removes your imbalanced nature of your data set, okay. So you can do it manually if you want to pass here some weights for each class, and you can also use this imbalance value. If you will not mention anything, it will default one none, and all classes will supposed to have weight 1, okay. So come back here. Now you have seen class weight parameter, random state. Random state, whenever we are using some random parameter, it is using to usually we use to reproduce our values. Okay, let's say for simplicity, let's say if I will ask you guess a random value. Okay, maybe you will guess some six value. Let's say six. After 5 days or 6 days, if I will ask you guess some random value, you on that day you may guess some random value as eight. Okay, now this day and after 5 days, both days you have guessed some random values, but this day random value is 6 and after 5 days you have guessed value 8. To make that the same random value that you have guessed today, it's also random, but the same value that you have guessed today, you should guess after 5 days also the same value. Then you can mention here the random state. In the same way, let's say you have trained your model and again you want to run your code. Okay, you have coded the all the model and all the stuff 1 year ago, and again you want to run the code. If you want to get the same type of model that you have like seen last year and the same scores and same type of data, you usually use the random state. Okay, so the purpose is that you restrict your randomness, that this random value that uh, you have gotten right now, same next time you should have same random value. So that's why this random state actually use this. And here in the case of solver SAG, in each iteration, SAG is picking just one instance. Okay, so it is picking random instance at each iteration. So for that purpose, random state is can be used and also can be used for the linear also. For the solvers, I have told you that there are five solvers there, and each solver have some restrictions according to some parameter values and some advantage according to some nature. Let's say here according to some behavior of your data. And if you want to study that which SAG, about SAG and SCGA, it's these are the gradient descent, and how the linear actually works in the coordinate descent algorithm. It usually use linear. Okay, and LBFGS. Uh, they have also mentioned here. Yeah, LBFGS is an optimization algorithm that approximates Broden-Fletcher Gold-Fobb-Shannon algorithm, which belongs to quasi-Newton methods. Okay, so it's recommended for use for small data sets, but large data. But for larger data set, its importance suffers. Okay, so anyhow, I also have not much knowledge about the maths behind that algorithm. But if some of you are interested in the maths of behind LBFGS, Newton CG, or liblinear, so you can refer these references. They are mentioned here in the documentation also. Mm, they should have here. Yeah, these references for the liblinear, you can refer this. uh, Reference for the LBFGS, you can refer this. SAG, you know already about SAG. If you want to interested how they have extend SAG into SGA, you can read that. And for the duality principle, you can also read that documentation if you want. Okay, but it's really not necessary for now to read these documentations. Okay, anyhow, here we have discussed solver. After solver, max iteration. In the logistic regression, we are using some gradient descent and this type of approaches. And in the gradient descent, we have some iteration. How many number of iterate our algorithm, or we want how much number of iterations in our algorithm, then we can mention in that parameter max iter some value. By default it's 100. It means 100 times your algorithm will run by default. If you will mention some other value, it will run according to that number of values. And they also have mentioned maximum number of iteration taken for solvers to converge. Okay, you can also specify it by yourself. And this can also stop your algorithm, and this value can also stop your algorithm, the tolerance. When you achieve some tolerance at some particular iteration, your algorithm already automatically stop there. Okay, so multi-class I have discussed also before, and later we will discuss in more detail what is actually OVR and what is multinomial. Verbosity in each almost in each models of scale and verbosity parameter are usually present. So for linear LBFGS, if you want to see the details during the training or running of algorithm, what is going uh, behind the code, what compiler are actually doing here, you can use their verbosity and how much detail you want to see during the training process. So for the linear LBFGS solver, set verbose to any positive number. Warm start, for now it's not necessary, but warm start is if you already have trained your model and you want to reuse that model, and with the change of some values, parameter values, you can use warm start. When set to true, reuse the solution of the previous call to fit as initialization. Njobs, it's a hardware related parameter. Number of CPU or cores used when parallelizing over class, if like a multi-class or OVR, when uh, uh, you want to use number of how many number of CPUs or CPU cores. So here, if you will mention none, none is by default. It's by default value of njobs. It means one core you want to use. If you will mention -1, it means all processor you want to use. If you want to see the details of n jobs, you can go glossy, but it's usually we mentioned to faster to limit our training. If we want to complete our training in short time, or in which time, or how much processing we want to use during our training. So that's why that parameter, it's a hardware related parameter, you can say. L1 ratio, I have told you L1 ratio to it's a how much ratio of one value or one penalty, and with respect to some other penalty, how much combination of L1 and L2 you want to use. Okay, like you can mention here 40 if here you have seen L1 ratio is equal to 0 means L2 penalty, and L1 ratio 1 means L1 penalty. Let's say if you will mention L1 ratio is equal to 0.4, then means 40% L2 penalty you want and 60% L1 penalty you want. So 40-60 ratio you want to use in your cost function. Okay. So in this way, this L1 ratio parameter works. So in the next session, we will discuss attributes and functions or methods provided by the Scikit Learn. So for now, thank you.